8 minutes. The time it takes the sun's light to reach us. 150 million kilometers at 300,000 kilometers per second. A rather insignificant distance, however, in relation to the size of the universe. But let's take a journey into the past. An imaginary voyage in time where we'll witness the birth of the universe itself at the time of the Big Bang 15 billion years ago. Particles from the very first moments of time. Protons, neutrons and electrons, of course, but also other much more energetic ones. These particles are preparing to interact and collide, generating others which will give birth to the stars. The end of this imaginary journey was not fictitious. Indeed, this collision, a real Big Bang, did actually take place 100 meters under the Earth's surface in an accelerator capable of propelling electrons at speeds close to the speed of light. Thousands of interactions per second involving the appearance of other particles are recorded, sorted and measured in CERN's laboratories. Among them, physicists hope to identify a new, very heavy and very energetic particle which has existed since the very first moments of the Big Bang. This is LEP's challenge, a giant circular accelerator 100 meters below ground near Geneva. Why this research? Because to discover the infinitesimally small also means understanding the great laws of the universe. Man, the eternal unsatisfied explorer, extends his horizons as far as the distant planet Venus with the Magellan probe. We have always been fascinated by celestial phenomena. Many theories have been expounded. When he discovered Jupiter's 4 moons, Galileo revolutionized the world by proving that Earth is not the center of the universe. Galileo's small telescope, an instrument fixed on the infinitely large, has today become the giant microscope, fixed on the infinitely small. This microscope is the CERN accelerator, equipped with 4 detectors which continually analyze the thousands of interactions provoked by the collision of particles. By 1983, the tunnel had been dug at a depth of 100 meters, a major feat of civil engineering, underground, through rock, and with millimeter precision. 27 kilometers of tunnel with 4 giant halls to house the detectors. Everything was done to guarantee the success of the project, including the installation of a small suspended train to ferry the various pieces of equipment. A veritable subway with underground halls 8 stories high to house the detectors. In the tunnel itself, a succession of pieces of apparatus to accelerate the particles and guide their trajectory. But how does the accelerator work? In a circle, 27 kilometers in circumference, electrons and positrons, grouped in bunches about 3 centimeters long, are accelerated in a vacuum to a speed close to that of light, 300,000 kilometers per second. Here we see 4 red bunches, positrons, traveling in one direction, and 4 blue bunches, electrons, in the other direction for a whole day. Thus the 8 bunches meet at various points, particularly in the detectors. Billions of particles are present in each bunch, but their small size and the vacuum surrounding them does not ensure 100% collision. That's why inside the tube, very powerful magnets concentrate the flux before it enters the detector. 11,000 turns per second and thousands of collisions in the 4 giant detectors, which are capable of recording in real time the trajectories and identities of the secondary particles emitted at the moment of interaction. The bunches of electrons and positrons also collide outside the detectors. To avoid useless interaction, electrostatic separators have been installed at these locations which deviate the trajectories. Today the accelerator is twice as powerful as it was in the beginning. But the electrons circulating in the accelerator are slowed down by the luminous rays they emit. As the energy doubles, the braking phenomenon is 16 times greater. To double the energy capacity of the accelerator and obtain a new type of interaction, the power of acceleration has therefore had to be increased 16-fold. Much more powerful acceleration cavities have been installed. Inside these cavities, an extremely powerful electromagnetic wave produces an electric field constantly switching from positive to negative. The positron is simultaneously attracted by the negative field and propelled forward by the positive field. The negative electron, which is not shown here, undergoes the opposite effect. As it passes through the cavities, the positron is accelerated at 6 million volts per meter. The materials used in the manufacture of the cavities have been specially selected to avoid any energy loss, which also means that the device must be maintained at a constant temperature of -269 degrees Celsius. That's why the cavities are sealed in a tube filled with liquid helium. The LEP's performance has been doubled. Its energy is now such that new families of particles which existed at the time of the Big Bang can be observed.